Now we are solving the group B questions of the previous question paper. The first problem from group B questions is from the population growth chapter. Question number 2, estimate the following for design population of 1 lakh and average 270 LPCD, average daily demand. So we have to find out the average daily demand, maximum daily demand, maximum hourly demand, higher demand and coincident demand. These are the demands we have to find out. Now, the solution is first the average daily demand. The formula for average daily demand is per capita average consumption, that is in liters per person per day, multiplied by population. So the average consumption, per capita average consumption is already given in the question, and population is also given. So we have to multiply these two. 270 into 1 lakh liters per day, then we are converting it into million liters per day, that is MLD. So we get the answer as 27 MLD. Next, maximum daily demand. We assume that 180% of annual average daily demand is our maximum daily demand. So 180 by 100 into 27 MLD, which we have found out earlier. The answer will be 48.6 MLD or million liters per day. Third is maximum hourly demand. It is also assumed as 270% of the annual average hourly demand is our maximum hourly demand. So 270 by 100 into 27 MLD, again we are getting as 72.9 MLD. Fire flow or fire demand. An equation is given for this fire flow, that is Q equal to 467 root P. P here is the population, root P into 1 minus 0.01 root P. So we are taking the population in thousands. So we are putting the value of P, that is population, here as 100, as we are taking it as 1000. So the Q comes out as 41733 liters per minute, and if we convert it into MLD again, that is million liters per day, that is we are multiplying the value into 1624 by 10 to the power 6, we are getting it as 61 million liters per day or MLD. Last is the coincident demand, which is the maximum daily demand plus the fire demand or fire flow. So we have got the maximum daily demand as 48.6 earlier. So 48.6 plus our 61 MLD, that is the fire demand. So we are getting coincident demand as 109.6 MLD, million liters per day. Now question number 3. Next question is the derivation. It is a derivation. Derive the expression for finding out the heat of an infiltration gallery. So this is the figure or flowchart. We have prepared a cross section of the infiltration gallery. This is our infiltration gallery. This is an elemental portion from the aquifer we are taking. This is our drawdown curve. This is the soil, and this is the actual flow pattern of the aquifer. This is the water level and the actual flow pattern inside the aquifer. The discharge from the gallery can be computed. We are computing the discharge of the gallery from the Darcy's law, that is Q equal to KIA. Darcy has given this formula, Q equals to KIA. Q is the discharge, K is the permeability, I is the hydraulic gradient we know, and A is the area. So now consider a point P with coordinates x, y. This is the point P in the drawdown curve with coordinates x, y. On considering a small element, we have considered a small element will be Ex. So the head gradient will be dy dx. This is y. So the head gradient is dy dx. And the y into L. This is y into L. L is the length of the gallery. Now discharge, putting this in the Darcy's equation, that is equal to KIA. K, in place of I we are putting dy dx, the head gradient, and in place of A, that is area, we are putting y into L. So after integrating it on both sides, we are getting x, integrating with limits x in left hand side, x equal to 0 to x equal to capital R, and in right hand side y equals to small h to y equals to capital H. We are getting, after integrating on both sides, we are getting this formula q equals to kl into capital H square minus small h square by 2r. This is the formula for infiltration gallery. Discharge of infiltration gallery, where K is the permeability coefficient of the aquifer, L is the length of the gallery, R is the radius of influence. You can see from the diagram or figure, R is the radius of influence, and capital H is the static water level above bottom of gallery, and small h is the depth of water in gallery on pumping equilibrium, that is, this is small h and this will be the capital H. This is the capital H here from the water table, height of the water table.